Yeah.
Okay. Yeah, you do not have to include 0 in your list of oxidation states. That's a given. Other questions? How'd we do on this? Yeah? Okay. Didn't miss one? If you did miss one, you know what you missed. You know what to watch out for. Remember, the big thing to do is after you write out that electron core configuration and box it off, what do you have to do, Alexa?
See if it's a metal or not.
Yeah, that's a big deal, guys. You got to know whether you're going to be losing only or losing and gaining. Yeah, you'll notice that for lead, I didn't give you the oxidation states, so let's go ahead and list those out. So for lead, you came up with what oxidation states, Hunter?
Lead. I messed up on this one, I didn't write it in final form.
Okay. Well, while you're figuring out what it is you messed up and coming up with your answer, that'll give Nova and Eric a chance to check their answers and everyone else to verify that they think they're right on what they got. Yeah, oh, by the way, Abby, argon, to your point, that's the only thing you could predict.
Yeah.
Yeah.
So would it be lead plus 2 and then lead plus 4?
There you go.
Filled S and a filled D.
Filled S and because you're going to be stopping at a filled S and stopping at a filled D. Correct. Those are the 2 oxidation states and the only 2 that you should have come up with. And if you look at the periodic table, oh yeah, that's kind of in keeping with what we know about lead anyway. Okay, plumbus and plumbous ion. Good. Questions at all? Yep.
For nonmetals, when you're losing electrons, do you lose the same number, like 7 and 8, as you would with normal metals? Can you lose the same number?
Yeah, the number of electrons, same rules apply for the nonmetals as they do the metals as far as losing electrons is concerned. Correct. Other questions? All righty, well, if you have no other questions, then it's a big day today because we are going to look at the other half of the chapter starting today. And what we talk about today, guys, if you understand it, you can understand the rest of this chapter. I'm talking about periodic trends. A trend, as you recall, is what? What's a trend, Eric?
Something that happens from like row to row.
So I asked you if some 8th grader comes up and says, "What's a trend?" You're going to say that something you're going to start talking about the periodic table to them. Okay, so what's a trend?
Just something that is popular among. I don't know.
All right, Michael, you finding it? You're laughing at him. Go ahead.
Is it a repeating series or a repeating pattern?
It's a pattern of some kind. Okay, a pattern of some kind. And when we talk about periodic trends, what we mean to say is that, well, shoot, I mean, I guess since this is about the we're talking about the periodic table, we should definitely talk about the periodic law. Remind me, you mean we still have to know that? That's not in the packet. Oh, well, you definitely, it's about periodic table. So, yeah, let's add periodic law to our list of things to know. Okay, so what does the periodic law state? What does Moseley's periodic law state? What elements are arranged? Increasing order of
Atomic number.
There occurs a periodic repetition of chemical and physical properties. And this is what this part of the chapter deals with. It deals with those periodic repetition. That is, every so often we see a trend emerge. And those trends are either going to be down a group or across a period of elements. So we're going to be looking at trends both going across a period and down a group as well. By the way, before I forget, a couple things came up last Friday when, after you guys left, someone was talking about hydrogen peroxide. If you remember, we did the predicted oxidation state for oxygen on page 7. We did that together as a class, and we came up with -1, +2, +4, and +6, right? Okay, so they said, well, what about hydrogen peroxide? Well, the hydrogen's +1, and you have 2 of them, so this means that this is +2 overall. Now this compound is just that, a compound, so it has no charge overall, which means I need -2, and since there's 2 oxygens, what's the oxidation state on each oxygen? -1. Well, we didn't predict that. Well, right, we didn't. But how stable do you think that is? Not stable. That's why hydrogen peroxide is so darn reactive. That's what makes it good at going out and reacting with things like bacteria and destroying them. Okay, it's extremely reactive because it's not a very stable oxidation state by any means for oxygens. It's very likely to break down. That's why you have to hold hydrogen peroxide in a brown bottle to stop the UV light from, causing its decomposition, because it's easy to get this stuff to break down. Questions? Okay, and you recall that the elements that already have a stable electron configuration are referred to as what again, Julia?
Noble gases.
Why do we call them noble gases? How many knew that we called them noble gases before this class? Oh, look at all the hands in the air. Did you ever wonder why they were called the noble gases? Because what?
They don't interact with the peasants who have
Excellent. No. All the other elements, they're going around exchanging electrons with each other and sharing electrons, and that kind of base activity is beneath the noble gases. They are of noble. That's exactly it, Kyle. You laughed at him. He was dead right. That's exactly why they're called noble gases, because they are nobility. They are beneath, such common activities of sharing and exchanging electrons, it's beneath them. No.
How do we call halogens halogens?
What's that?
What do we call halogens halogens?
I don't know. I'm guessing it comes from the Greek, and I don't know what the etymology is behind it. I'm imagining it's Greek. It could be Latin, but I don't think so. But that's a guess, and I honestly don't know. The noble gases, though, I thought you ought to at least know what they're called noble. All right. So what I'm about to talk to you about today is the things that determine periodic trends. What we find is the same factors that affect one periodic trend, such as atomic size, also play a role in things like ionization energy or electronegativity or reactivity. In other words, guys, if you understand what I'm talking about today, you are in awesome shape, because we use that same logic, that same information, to go back again and again to explain every single one of these deviations. So if you understand today, this rest of this chapter starts to fall into place. I'm not saying that you shouldn't memorize. There's an advantage to doing that, but you need to be able to explain these trends. It's not enough to simply be able to memorize them. You want to be able to explain them as well. In order to go ahead and account for the periodic trends, one thing that you have to understand influences them is the stability of the electron structure. And we've already looked at that. So you're already familiar with what constitutes a stable electron structure. But there are other things as well, and you can see listed, and this is on the, if you're not already there, turn past the page 7. So you're turning past page 7. You'll see there's that last worksheet on the opposite side of page 7. And we're on to the next one, and this is Coulomb's law. And yes, Coulomb's law is the same Coulomb as what electrical charge, the basic unit for electrical charge. Coulomb's law says F is equal to K times Q1 times Q2 over R squared. And it's basically talking about the force of repulsion or the force of attraction is directly proportional to the charge of the particles involved. Q1 and Q2 are the charge of the particles. And inversely proportional to the square of the distance separating those charges. So, what this really says is this. I mean, and if you think about it, you already know Coulomb's law qualitatively. You know that if you want really strong force of attraction, okay, which do you think is going to be more strongly attracted to one another? A +1 ion with a -1 ion, or a +2 ion with a -1 ion? Which of these two do you think would be more strongly attracted? This guy and this guy. Which of these two? Here's choice 1. Here's choice 2. Which one do you think involves a stronger force of attraction? Who said 1? Okay, so you said 1. Here's what I want to ask you, Michael. Why do you think the -1, okay, you understand the -1 is attracted to a positive thing? Okay, so do you think it would be more attracted to a plus 0.04 charge?
Right, I was thinking like like with elements, they want to complete their.
I'm just talking about force. This all Coulomb's law deals with is force of attraction. Now Michael's thinking, he's thinking along the lines of trying to, like, you know, electron structure. That's something different. Alexa, do you understand?
Yeah.
Okay, and the whole reason why they're attracted because they're opposite charge. So what we're saying is the greater the magnitude of charge, the stronger the force of attraction. You would expect +2 and a -2 ion to be more strongly attracted than, say, a +1 and a -1. You would expect a +2 ion to a -3 ion to be more strongly attracted than a +2 to a -2. You guys with me? All right, so that's what it's saying qualitatively. It's also saying that the greater the distance that separates those ions, the weaker will be the force. In other words, the closer I get them, the stronger the force. And if you think about magnets, that kind of makes sense. I mean, I don't care whether you have the magnets set up to repel one another or set them up to so that they are attracted to each other. When do you feel the repulsion and the attraction most severely? When they get further apart or when they get closer together? And that's all Coulomb's law is saying. Is like, look, the force will increase the closer they get to one another. And this is true for the ions too. Okay? A +1 ion and a -1 ion are going to feel more strongly attracted to one another when they're this far apart, as opposed to, you know, when they're separated by a greater distance. So this is something that you're already kind of familiar with on a qualitative sense. Okay, it should be something that's not too difficult. Coulomb's law is something that we're going to be coming back to again and again. If we look at Coulomb's law in terms of how it relates to the atom, what are my charged particles? Because we're not dealing with ions, so what are my charged particles? Well, we have two things. One thing we have to consider is the charge of the electron, the other is the charge of the nucleus. Now, Q1, that's the charge of your electron. And if Q2, the charge of the nucleus, normally would be good enough, however, it's not sufficient. It's not just simply the charge of the nucleus we have to look at. And I'll explain to you what I mean by that. I find that if you do this pictorially, it's helpful. So you're going to see me do the following as I go through. I'm going to be going ahead and we'll look at just nuclear charge to start off with. The charge of the nucleus. What determines how positively charged the nucleus is? Matthew? Number of protons. So, and we know that Z represents the atomic number, which is the number of protons. So when we talk about nuclear charge, we're really talking about Z. And there's a trend. As you go across, and I like to do this pictorially like this, it's easier to memorize that than a couple of sentences. So, and it'll make it easier to see patterns among some of the trends that we're looking at. You can see which ones do the same thing, and that helps to also, you know, commit this to memory. As I go across a period, what's happening to my nuclear charge? Maria? Yeah,